Good thing I have the remote. The ladder problem. So we're going to do static equilibrium with the ladder problem today. So ladder problems are just that. It's usually a ladder leaning against a wall. Now we are going to do the frictionless wall, make our lives a little easier. And we're going to go ahead and we're going to try and find the coefficient of friction needed on the ground so that our ladder doesn't slide out from underneath us in terms of that angle, theta, that we lean our ladder up against the wall with. So because it's static equilibrium, I know it's static equilibrium because my ladder, I want it to stay there. It's not going to accelerate in the y direction, the x direction, or rotationally accelerate. So because I know about those accelerations, I can say the sum of the forces in both the x and y is 0, and the sum of the torques is 0. So the first thing I need to do is I need to generate my free body diagram. So let's think about what forces are acting on here. So I do have gravity, and remember with objects with size, if it's a uniform ladder, which ours is in this case, the force of gravity acts at the center. Okay? The other force is acting here. It's touching two walls, so each wall has a normal force. I'll call this one N, and maybe I'll call this one NF for N from the floor. And there's one other force here. We got friction. Friction is keeping the ladder's bottom from sliding out. Okay? And again, I said a frictionless wall. If there was friction, friction is trying to keep that ladder up, but we're not going to do that in this case. Now here's one extra trick we do for a ladder problem. It doesn't tell us the length of the ladder, so what we do is we call the whole ladder a length L, and then we refer to distances as fractions of L. Okay? So L over 2, and you can add people. You could say, hey, there's a painter climbing up there. The painter climbs 3/4 of the way up. What kind of coefficient do I need? And so, maybe this would just be L over 2, L over 4, L over 4, and I'd have that painter's mg pulling down. All right, great. So let's go ahead and set up our force equation. Since everything is nice in the x and y direction to start with, we'll do those. So in the y direction, I have normal force from the floor minus mg, the weight of the ladder, equals 0. In the x direction, I have friction and normal force. So I have normal force minus the force of friction equals 0. So we are going to try and find the coefficient of friction, which is sitting inside that force of friction. Okay. All right. And then our torque equation. All right. So in order to find mu, I'm going to have to say, well, normal force is equal to mu mg. So it's in there. So I need to know the mass and I need to know n. Ooh, that's trouble. And I got that n right here from the normal force on the floor is equal to mg. And remember, just a quick reminder here, this is mu times the normal force from the floor. This is our static friction here, reaching a maximum value. So I want to find the minimum mu value. All right, so let's create a torque equation. So what I'm going to do is I'm going to go ahead and choose my axis of rotation right here at the bottom. The reason I'm choosing it here is when I create a torque equation, these two forces are not in it. Now I do know what you're thinking. You're saying, hey, but the mu we're trying to find is in the force of friction. But if I can figure out what this normal force is in terms of mg, I can make that substitution. My mg's will hopefully kind of cancel out, and I'll be set just with theta. So let's go ahead and see what happens here. So I am going to have to, in order to create a torque equation, find these values perpendicular. Now I like to make it perpendicular to the ladder. It makes a little more sense to me. So I'm going to find these perpendicular components. Now you can think about, those triangles. I'm not worried so much about these components with the dashes because they're parallel to the ladder, so they're not going to produce any torque. All right. So this one here, this is my angle theta. This is also my angle theta. I like to keep the angle the same as the one I'm in charge with. And so this one's going to be mg cosine of theta. This one here is going to be n sine of theta. Now the other thing I like to do is I like to identify, is it a positive or a negative torque? So what I'll do is I'll just set my ruler or my pencil on there and I'll pretend like I'm that force and I'll say, is it rotating it clockwise or counterclockwise? And so in this case it's rotating it counterclockwise. So that's going to be our positive torque here, meaning the other one's going to be negative, but you could also use your right hand rule. Okay, so you get out your little physics gang sign, you point in the direction of r, then your middle finger goes in the direction of the force, so my n sine theta is that way, so my thumb points into the board, meaning I have a negative torque. So you can do that as well. So that one's negative, that one's positive. All right. These two produce zero torque because the R is 0. Okay. So let's go ahead and generate our torque equation. So I have mg cosine of theta, and it's positive times how far away it is, L over 2, minus n sine theta times its distance, which is L, is all equal to 0. Now, this is that trick for ladder problems. They typically won't give you the length. They'll probably give you where things are, like relative, like 3/4 of the way up, 2/3 of the way up. And that's because those L's cancel out for us. Okay? So I have one equation equal to n here. I'm going to get another equation equal to n there, and then I'm going to kind of put them next to each other, set them equal. So solve for n. So I have mg cosine of theta divided by 2 equals n sine theta. Divide the sine of theta over. So I have mg times cosine of theta divided by 2 sine of theta equals n. We're going to set these two things equal. So I have mg cosine of theta divided by 2 sine of theta equals mu mg. You'll see the mg's cancel. And I just have thetas left. That's a good thing. So I can either turn this into cotangent over 2 or 1 over 2 tan theta. It's up to you. I'm going to do 1 over 2 tan theta is equal to mu. And so there we have it. We have the coefficient of friction, the minimum coefficient of friction needed at an angle theta to support our ladder against a frictionless wall. Okay? And again, if you have a painter or someone climbing it, you're just going to have one more torque in here. And they'll probably put the mass of the painter in terms of the mass of the ladder. Things will cancel if it's going to be a variable only question. There you go.